Dear students, I welcome you for the today's lecture related to the boundary layer concept in the convective heat transfer phenomena. Now, the boundary layer, all of us have studied the fluid mechanics subject, and in that fluid mechanics, it is the application of that fluid mechanics or understanding of the fluid mechanics, and we are applying those basic concepts for the heat transfer and specifically for the pipe as well as for the flat plate. Now, how the flow variation that can be there when the flow variation that exists. This flow variation and a certain boundary that is formed. Now, there are the two boundaries that we are going to consider. That is, one is the velocity boundary, and this is also called as the hydrodynamic boundary also. Velocity boundary layer or hydrodynamic boundary layer. And the second one, that is the thermal boundary layer. So two boundary layers, we are considering this aspect of heat transfer. So we are considering the thermal boundary layer also. Now, this is the why we are studying this is to understand the mathematics associated with this. When we study the advanced fluid mechanics, that is computational fluid dynamics concepts, there you must have the understanding of coefficient of the friction, drag coefficient, no slip velocity condition, the stresses, the shear stresses and its all flow variations, the continuity equation, the momentum balance equation. All this is needed to understand and analyze the different flow situations in the fluid mechanics as well as in the heat transfer and in mass transfer. So this fluid itself, how this fluid that is going to behave and its behavior that is going to affect your heat transfer processes as well as your mass transfer processes. And so this understanding of fluid mechanics or the hydrodynamics is very much essential. And to simplify those equations, when you do the mathematical analysis, you require to understand the basic concepts of this fluid mechanics. So there are velocity boundary layer and the hydrodynamic velocity boundary layer or hydrodynamic boundary layer, and the second is the thermodynamics boundary layer. So for this boundary layer, that is the region near the body. Now any region, a thin small region near the boundary, that can be considered as the boundary layer. We have considered the different heat transfer coefficients, right? Now if it's a vertical plate that exists or a horizontal plate that exists, now in this, the fluid which is moving in this direction will be in contact just close to this plate. This is the close contact of this plate, and this layer of fluid, which is in very close contact with any stationary wall, that is forming a certain thin region near this body, that is called a boundary layer. And this boundary layer, that is because of the velocity as well as temperature gradient that exists in this boundary layer. because of the existence of gradient differences in the temperature as well as differences in the velocities that exist, drastic differences that exist, and that is why it is essential to study this. So this velocity and temperature gradients, they are very large, and it becomes essential to study it when we do the detailed analysis. And the region which is outside this boundary layer, where the velocity and the temperature gradients are nearly equal to their free stream velocities. That is nothing but the velocities and the temperature in the bulk region is uniform, that is same as this velocity. That means there is a temperature gradient, velocity gradient in the surrounding of this plate and in the bulk region. So this temperature gradient or this velocity gradient leads us to study this topic of the boundary layer. There is a free stream velocity. What is free stream velocity? That is the uniform velocity which we are considering. Average velocity we are considering. That is the free stream velocity. So the thickness of this boundary layer has been arbitrarily defined and a certain distance from this surface. Now, to calculate this boundary layer, what will be its thickness? What will be its x direction length, and what will be its y directional thickness when we are considering the horizontal plate? This discussion we are dealing and it is better to understand when we keep a horizontal plate. So to have this understanding of this thick boundary layer, that is nothing but it's a arbitrary, imaginary, and we are going to study this boundary layer. Now look at this basic figure. This is the development of the boundary layer on the surface. So we are considering a plate. This is what? A plate, stationary plate that is considered. And before the entry of this plate, we are assuming a uniform velocity v of the fluid. This velocity v is uniform throughout, and that is why all these velocity vectors are of a constant length. All these velocity vectors are of a constant length, that is not changing. So velocity is considered to be the uniform at the entrance of this plate. So now this plate is being hit by the fluid. Now consider that this is our plate, and the fluid which is coming in this direction will have the uniform velocity. Now the fluid which will hit at this end will be stationary, will be having zero velocity when the fluid hits. Before this part, it is having the uniform velocity. ऊपर की भी यहाँ पे पूरी throughout velocity is constant. But when this fluid that hits at this point, its velocity becomes zero. So we are going to consider this velocity at the surface that will be the zero, that is this point. This is the velocity we are considering as the zero. So this is the contact with the surface. Surface के साथ contact हुआ है, There you can see the velocity as the zero at this point. This is the first understanding. Why velocity is zero? When the liquid particle hits the solid surface, there is no forward movement. It may take the different path and then can get the velocity, but at a moment it is going to stay stationary. So the velocity on the surface that becomes zero. That is the first point. So then the non-slip condition that is assumed. That is one of the assumptions. Due to the no slip conditions to be satisfied at the surface of the plate, the velocity of the fluid that is reduced to the zero relative to the surface. That is what we have talked. Now, this results in retardation of the fluid particles in the adjacent layers, fluid layers. Now, once this velocity becomes zero, it is going to offer the resistance. Now the velocity at this point is zero, on this surface it is zero, so which is the layers above this is going to offer a certain resistance. So this layer is going to offer a resistance for this layer. This layer is going to offer a resistance for this layer, and as a result, because of this shearing action, because of this viscosity effects or viscous forces, this is because of the viscous forces, this results in the retardation of fluid particles in the adjacent fluid layer is because of the shear stresses. Shear stresses, that is nothing but your mu du upon dy. Shear stresses tau, which is equal to mu into the du upon dy. So these are your shear stresses. They are proportional to your viscosity, and minus sign is there, and proportional to the gradient of velocity in the y direction. Gradient of velocity in the y direction. We are considering this shear stresses in the x direction. So the shear stresses in this x direction, there is a velocity gradient in the y direction. This is our y direction. So there is a velocity gradient in the y direction that will be observed. Understood this point? Velocity gradient in the y direction that is observed at this point. Because the zero velocity at the surface that is existing, on the subsequent layers there is a gradient that is observed because of the inside shear resistances, inside fluid resistances caused because of the viscosity, and the velocity gradient in the y direction. So this is going to have the certain gradient in the lower region, and after that it may attain the same uniform velocity as that of the inlet region. So this region where the velocity gradient exists is of our concern. We are going to study this velocity gradient. Why velocity gradient that is existing is because of the shear stresses, fluid's internal stresses. Fluid internal stresses is because of the viscous forces that is going to offer the resistance in all the subsequent layers. एक लेयर में है, फिर दूसरे लेयर में रेजिस्टेंस ऑफर हो रहा है, फिर तीसरे लेयर में रेजिस्टेंस ऑफर हो रहा है, एंड दिस रेजिस्टेंस इज गोइंग टू डिक्रीज, एंड दैट इज व्हाई यू आर गेटिंग अ वेलोसिटी ग्रेडियंट वेरिएशन, कर्वेचर मिल रहा है वहां पे, that is of concern. This deceleration of the fluid particle in the boundary layer is associated with the shear stresses. The effect of these shear forces originating the surface extends into the body of the fluid, but with the increasing distance also. That distance is in the y direction. Now coming to this second figure, now here we have seen the velocity gradient that is going to observe. Velocity gradient is going to observed in this region. Now we are trying to observe, here the velocity gradient is there, and look at this velocity gradient at a distance x. In the x direction we are having the different velocity gradients, velocity profiles. यहाँ पे एक certain layer है और यहाँ पे एक दूसरा layer है. Why that difference exists? That is, the effect of the shear forces originated at the surface extend into the body of the fluid. With an increasing distance y from the surface, and the velocity component of the u increases until it approaches a free stream velocity, that is u infinity. So u infinity is nothing but your v, or you can say this is u infinity, the average value, or v, whatever the notation. In certain books it is v, it is certain books it is u infinity or u maximum also. So this gradient that exists. Now this boundary layer thickness is typically defined as a distance y from the surface at which u, which is equal to 0.99 v, or which is equal to 0.99 into u infinity also, whatever you define, that whether it is a v or u infinity. So u, the typically means actual velocity u here. When the fluid which is heating to the surface, which is heating to this plate at this end, having the zero velocity, and attains a certain velocity here, and this layer goes on increasing as the variation of du upon dy that exists. That is going to vary. So why variation is observed? Shear stress at this point, shear stress at this point, they are going to be different. So coming, what will be the boundary layer thickness? Delta is defined as your boundary layer thickness. Boundary layer thickness at this point is this delta, at this point it is this delta, at this point it is this delta, at this point it is this delta. So this boundary layer thickness is going to vary, and it depends on the distance x. So as we are going to increase from the inlet region, it will attain a certain increasing delta value, and after attaining a certain value it remains a constant after that. So a suitable delta value that has been obtained and it will remain constant. But in this inlet region it may vary. Now why it is going to vary in this inlet region? That is because of the laminar turbulent flow conditions. So when we talk related to the laminar flow conditions, initially this velocity that is of a laminar flow condition, uniform flow condition that is existing. So in the inlet region, you can see the laminar flow that has been observed. Then slight turbulence that is started in this transition region, and then a chaotic condition that can be observed in the turbulent boundary layer region. So in this boundary layer itself there is a thickness variation what we have considered depending on the distance x. Depending on the distance x, this boundary layer has the different values of the thickness. Here it is certain delta, here it is certain delta, here it is certain delta. So this delta, this boundary layer thickness is going to vary with the distance x, and it is defined as u, which is equal to 0.99, the u maximum or the u average. So 99% of your u average that has been attained, that is your boundary layer thickness. That means you have attained, at this point the velocity attained is 0.99 velocity, the u maximum. At this point the velocity attained is 0.99. At this point the velocity attained is 0.99. So this is the, and this is the hypothetical line, imaginary line. This you cannot see it visually. It is all done for the mathematical understanding. And this divided into the boundary layer region. The viscous effects are the velocity changes are significant in this region, and that is why this is going to observe. So this is because of the frictional shearing stresses, that is tau, which is equal to mu into du by dy that is existing. Then this thin boundary layer region near the surface in which the friction must be considered. Friction that is to be considered, and the outer region where the boundary layer, the frictional effects that can be neglected. So near this surface your frictional effects they can be considered, and however in this bulk region the frictional effects they can be neglected. This is for the doing simplification of the mathematical understanding of this fluid mechanics problems. All this is defined by the scientist Randall, and this is the skin coefficient friction that is needed to be studied when we consider the frictional factor. So you require to understand the skin friction coefficient. Skin friction coefficient that depends on your shear stress, viscosity and the velocity. And after the calculation of this friction coefficient CF, you are going to calculate the drag forces. That is what the next step we can study it. The coefficient, skin friction coefficient and the drag friction, that is also needed to be studied. Now as we have talked that this is the laminar layer transition region and the turbulent region that exists in this region. Now what happens in the laminar region? That is the uniform velocity vectors, they are moving. Velocity vectors are uniform, steadily, they are in parallel direction. However, in turbulent region, they are in a chaotic condition. This is what you can observe, the chaotic condition that is observed here. And here they are uniform. Now, when you go into the details of this turbulent boundary layer, you can have the different sublayers also. That is the viscous sublayer, buffer layer, overlap layer, and turbulent layer. In this region of laminar boundary layer, it is the viscous sublayer that exists in the initial. Here on the surface, the viscous sublayer that exists, above that a certain buffer layer that exists, and after that it's a turbulent conditions that has been observed. Now when you see this viscous sublayer, the velocity gradients are very high. If you magnify this part here, you can see this sublayer, the velocity gradients, velocity values. These arrows indicate the numerical values for the velocity. छोटा एरो है तो वेलोसिटी उसकी छोटी है, बड़ा एरो है तो उसकी वेलोसिटी बड़ी है. That is what the velocity vectors represent with the numerical values. When you calculate it with the help of computational fluid dynamics, for example, in case of your Fluent softwares or any other CFD softwares, you can see the different velocity vectors and they are having a specific magnitude, specific value for that velocity vector that exists. So छोटा velocity vector है तो उसकी magnitude, उसकी numerical value less है. And that means in this sublayer, viscous sublayer, the smaller or gradient is high. Variation in the velocity is high because of this viscous sublayer. Then slightly in the buffer region, that variation decreases. You can see this curvature, this section of the curvature. That is your buffer layer, where you can note down the velocity gradient that has been decreased. Initial part, velocity gradient is more. यहाँ का portion जो है velocity gradient more है. Then in the buffer layer, velocity gradient is less, and after that the velocity gradient is more or less same. Velocity gradient is more or less same. That is what the velocity profile in the turbulent region is more flatter. More flatter. That is what uniform. यहाँ पे जो velocity gradients है, they are flatter, they are uniform. Here the velocity is flatter velocity profile you get. This is what a flatter velocity profile. Here also in this section, upper section, you can see the flatter velocity profile. However, in the lower section, you are having a slight curvature that exists. So this velocity profile in this turbulent region is more flatter than in the laminar region. So this is what the existence of this boundary layer, why this boundary layer exists, that is because of the friction and the fluid internal forces. That is because of the shear stresses that depends on the viscosity, and this boundary layer that is defined as the layer up to which the velocity that is obtained is 0.99 v. So this velocity boundary layer, the region of the flow above the plate boundary by delta, in which the effects of the viscous shearing forces caused by the fluid viscosity are felt. Then these shear stresses for viscosity liquids, that decreases shear stresses. So this is what TW, mu into du upon dy at y is equal to 0. Mu is your dynamic viscosity. Then this is the CF is the friction coefficient that exists. CF is your friction coefficient that exists, and you can calculate the friction coefficient, and after the calculation of friction coefficients, it's a drag force that can be calculated. Now coming to the thermal boundary layer, and in case, okay, now coming to the thermal boundary layer. This thermal boundary layer, the uniform temperature that has been observed, T infinity is my bulk temperature. T infinity is your bulk temperature, and the Ts is your surface temperature. At this point, it's a surface temperature, which is the Ts. And this is what? The T infinity. Now similarly, you have to assume a certain plate, and on which the fluid that is entering from this side, from one side, this is having the uniform temperature throughout. Now considering that this plate is at a lower temperature, this figure shows the temperature of the plate that is lower. Ts is the surface temperature of the plate and bulk temperature that is there. Surface temperature and the bulk temperature. Surface temperature that is there and the bulk temperature that is there. Uniform fluid that is temperature existing. So this surface temperature is less. This plate is colder and the bulk temperature is the higher temperature. So here also the temperature gradient that exists. Now this delta T is your thermal boundary layer. Hydrodynamic boundary layer is only delta. Thermal boundary layer is delta T, or sometimes hydrodynamic or velocity boundary layer is delta or delta H also represented sometimes. Thermal boundary layer, that is delta T, that is represented. So this thermal boundary layer develops when the fluid at specified temperature flows over a surface that is at a different temperature. That is what we have defined, Ts and T infinity. Temperature difference that exists. Then this thermal boundary layer, that is the flow region over the surface in which the temperature variation in the direction normal to the surface is significant. Temperature variation in the direction normal to the surface is significant. So this temperature variation is significantly observed. Now the thickness of this thermal boundary layer that exists, that is delta T, at any location along the surface is defined as a distance from the surface at which the temperature difference T minus Ts equals to 0.99 T infinity minus Ts. We have defined this Ts Ts is the surface temperature and T infinity is the bulk temperature. Ts is our surface temperature and T infinity is the bulk temperature that is there. And the in between, it's a temperature T that is going to vary. This is what? The T. Now this temperature gradient Ts minus T, that is equals to 0.99 Ts minus T infinity. So at this line, the temperature difference is 0.99 T infinity minus Ts on this line, and this is the temperature T inside this. So the thickness of thermal boundary layer increases in the flow direction. Here also the thickness at this is this. At this point the thickness that is increased. The thickness of a thermal boundary layer increases in the flow direction. Since the effects of heat transfer are felt at a greater distance from the surface further downstream. Initially it's a uniform temperature. So यहाँ पे velocity zero होते जा रही है, तो velocity gradient exists and correspondingly the temperature gradient also exists. So the shape of this temperature profile in the thermal boundary layer dictates the convection heat transfer between the solid surface and the fluid flowing over it. That is a convective heat transfer between the solid surface and the fluid flowing over it. So this is related to the thermal boundary layer. Now this thermal boundary layer, that is also we will see a small correlation with that. Okay, this is the boundary layer concept, that is that is what this temperature correlation that exists, that is Ts minus T upon Ts minus T infinity, which is defined as theta upon theta infinity, which is equal to 0.99. Then the conductive heat transfer that is taking place just on the surface. At the surface there is no motion, the fluid is stationary. As the fluid is stationary, so there exists a conductive heat transfer, and this conductive heat transfer or the heat flux having the units of watts per meter square, Q upon A, capital Q upon A, that is the heat flux, which is defined as the Qs, and this heat flux that is equal to K into the delta T upon delta Y, and the convective heat transfer which is given as Qs, which is equal to H Ts minus T infinity in the bulk region. On the surface it's a conduction that is taking place, and in the bulk on the surface it is the the fluid is stationary, and so it is the conduction that is taking place. However, in the bulk region it is the convection that is taking place. So heat transfer from this point is by the conduction, and then in the bulk by the convection. So you can equate these two, that is H, which is equal to Kf into delta T by delta Y at Y is equal to 0 upon Ts minus T infinity. Since Ts minus T infinity is a constant and the boundary layer thickness delta T increases with the increasing x direction. X direction में delta T increase हो रहा है. So this delta T upon delta Y must decrease with the increasing x. Now when you talk in terms of the heat transfer coefficient, this is the boundary layer thickness and the heat transfer coefficient for the plate. Heat transfer coefficient and the boundary layer thickness. So in the initial region, that is in the laminar region, heat transfer coefficient that decreases in the laminar region as well as in the turbulent region also. But however, in this region of transition, there the heat transfer coefficient drastically increases. Similarly, the delta thickness that continuously increases from the surface thickness of your boundary layer, delta. So thickness that increases, these regions that is showing a laminar region, a transition region and a turbulent region that has been observed. So the fluid flow over the hot plate temperature field is set up, shows the temperature distribution. A thin layer of the fluid is heated by conduction in the region, thickness delta. This is only of our concern, these points. The thickness delta of a boundary layer is defined as a distance in y direction at which Ts minus T upon Ts minus T infinity is equal to 0.99. This one point is more important, and the thermophysical properties of the fluid affect the relative magnitude of the delta and delta T. Now how this is going to affect? This is the hydrodynamic boundary layer and this is your thermal boundary layer. Thickness of the thermal boundary layer, thickness, and it depends on the thermophysical properties. Prandtl number is nothing but PR, which is equal to Cp mu upon K. So if the values of Prandtl number is less than 1, the thermal boundary layer is higher, predominating. Then for Prandtl number which is equal to 1, thermal boundary layer and the hydrodynamic boundary layer, they are equal. And for Prandtl number greater than the 1, thermal boundary layer that decreases. That is Prandtl number which is equal to 1, delta T which is equal to delta. That means the thermal boundary layer and your hydrodynamic boundary layer, they are same. Prandtl number greater than the 1, the thermal boundary layer is less than your hydrodynamic boundary layer, and Prandtl number less than 1, your thermal boundary layer is greater than the hydrodynamic boundary layer. This is what figure wise representation, this is what numerical wise representation that is observed. And Prandtl number is nothing but your Cp mu upon K. That is what your thermophysical properties, they are defined. Now also we will see some specific properties of the hydrodynamic boundary layer. The heat transfer occurs due to the heat conduction, so the heat transfer coefficient depends on the thickness delta of the layer. This boundary layer thickness delta is a distance from the leading edge to the point where the U is within 1% of the U maximum. 1%, that is what? 0.99 U maximum. This thickness delta is dependent on the fluid properties, density, viscosity, surface tension, velocity, etc. And these are the laminar up to 10 to the power 3 and transition 10 to the power 5 and the turbulent layer as shown. So these laminar sublayers are formed